Okay, so in this video, let us discuss numbers. Okay, so basically, whether you like it or not, numbers do make your life a lot easier. When you go over to when basically in the old times, okay, when there used to be like nothing of the modern world, prehistoric world. Yes, let's go over to the prehistoric world when nothing was there. Okay, so at that time numbers were not invented. Okay, for those of you who don't actually know these things, the numbers, all these numbers, these are actually an invention. Okay, these are an invention of the humans. Okay, and we have actually benefited a lot by these numbers. And the reason why there are so many sets of numbers, why there are so many groups of numbers, is basically because numbers grew with with necessity, and how with necessity basically. So if you actually talk about the set of natural numbers, which is denoted by n, okay, it's actually denoted by n, and the numbers include 1, 2, 3, 4, 5, and so on. You know, these dots actually mean that they are continuous. They move like 5, 6, 7, 8, 9, 10, 11, 12. You know, so if a shepherd, okay, let's talk about a shepherd. A shepherd in the prehistoric times didn't have numbers. Okay, we're going to assume the people didn't have numbers, which is actually a true assumption. They didn't have any numbers. So when they didn't have any numbers, they if a person, okay, a shepherd went with his sheep, okay, a normal shepherd has like 30 or 40 sheep depending on the shepherd, you know. So if he has like 30 or 40 sheep, we can actually say there are 30 and 40 sheep, but that guy is like, those are my sheep, okay, those are my sheep. He can't actually count them. Numbers do not exist. Okay, so numbers should actually make our lives easier. Okay, that is the whole point of numbers. If they don't, you should actually start reconsidering. They actually do. They actually always do make sense. Okay, so talking about the shepherd wants to make sure that all of his sheep come back in one piece. All of his sheep, 30 sheep, come back in one piece. So what he basically did before the numbers existed, instead of natural numbers, basically, he would actually have stones. He would actually use stones to basically to be able to count in a different way. Like every stone, he would actually represent a sheep. So when all the sheep came back, he would be like, okay, one stone out of the way, 2 stones out of the way, 3 stones out of the way, and that is basically how they would go about their way. So after a while, when these numbers actually started to grow, they started to make a whole lot of sense. Natural numbers. He could actually start using just numbers. I have 40 sheep. Why do we have to have a whole area of stones when you can actually just say I have 40 sheep? He starts counting. Numbers is making his life easier. Okay, so when numbers, so that is how natural numbers came into existence. Now imagine a person doesn't have any sheep. How would he actually describe that? So basically, hence zero was invented. So zero was invented, and this is basically the way you can actually remember all these sets, like the set of natural numbers. And this is the order in which I believe they were developed. Like natural numbers, set of natural numbers 1, 2, 3, 4, 5. The set of whole numbers denoted by W, we just added the 0. The set of integers, Z, that is denoted by Z, includes 0, plus minus 1, plus minus 2, positive and negative 3, positive, negative 4, and so on. We have just added the negative numbers over here. Imagine a person went into debt. If you went into a debt, how would you actually explain that? I am $40 in debt. He would, so basically like that. If the shepherd was like 40 sheeps in debt, how would he explain that? Negative 40, right? So that is how basically the negative numbers came into existence, because of the need arised, the need, so the next set is the set of the rational numbers. The rational number is denoted by q, and x over y, they are written as x over y. These are the general terms. X over y is equal to p over q. These are the actual numbers, like this could be 4 or this can be 5 and stuff, and like that. So p over q, where p and q belong to integers. Okay, this is the symbol for integers. If you don't know what integers are, if you actually don't know what z stands for, this is the actual stuff I had to go through. These are the problems that you actually have, because when you are studying rational numbers or anything like this, where they just say belongs to like integers and stuff, and you have to actually know what integers are. So integers, as you have seen, 0 plus minus 1 plus minus 2 plus 1 minus -1 plus positive 2 -2 and stuff like that. So all of these are integers. P over q has to be an integer, and y should not be equal to 0. If it is equal to 0, all of this term just becomes infinity. So over here, when the set of rational numbers was invented, whenever it was, we have basically added the decimals in the whole group. Okay, now all of these groups are basically normal groups, like normal group of people, you can say. Basically, the thing is the same. The set of rational numbers q, as I've actually explained, the set of irrational numbers, those are denoted by q prime. Okay, that you just put the dash over the q, and they are basically denoted by x over y. The general term is not equal to p over q. These p over q can they should be any number where p and q belong to integers and y is not equal to 0. Okay, this is basically this basically tells us that this should not be equal to infinity or something. We are basically restricting the thing from becoming what do you call that? From becoming infinity. Yes, from becoming infinity. We do not want this thing to become an infinity. That is why both of these conditions are added. The main thing is this: p over q belong to integers. If a number cannot be written in this form, but both p and q should be integers, okay? They should be integers. If they can't be written like that, then they belong to irrational numbers. Pi is a very famous irrational number. Okay, 2 point what was that? Pi. Yes, sorry. The pi like 3.146 something. It doesn't stop. It doesn't actually stop. They may actually teach you that you can actually write it as like 7 or 14 or something on those lines. But that you have to remember is basically an approximation. That is an approximation. You can't have the exact value of pi. So continuing forward, these were the set of rational numbers. The set of real numbers. So what are real numbers? All real numbers basically, when you add both of these, okay, the decimals of both type, okay, rational numbers and the irrational numbers, when you combine both of these, you get real numbers. Okay, consider 2. Okay, consider 2. Where is 2? There you go. There, that's 2, and that's 2. So natural numbers, whole numbers, and integers all have 2. Okay, now consider 2. If you write 2 and you write 2 divided by 1, that equals 2. If that is actually equal to 2, that means that almost all numbers are real numbers. Okay, right? 2.5 is a real number, 2 is a real number, 3.5 is a real number. So basically all numbers, basically most of the numbers are real numbers. All of the numbers that belong to these sets are real numbers. Okay, that is what this basically means. Now, for those of you who actually do know complex numbers, the set of complex numbers, if you don't, no need to worry, you will sometime in the future. Set of complex numbers are denoted by C, and they're basically written in this form. For those who know, x plus iota y, this is the real part, this is the imaginary part, where this is like nothing, where x and y belong to real numbers. Okay, x and y need to belong to real numbers, and this added iota, which is actually equal to under root -1, this makes the whole stuff complex, you know. That is what makes it complex. So moving on, these are basically all the you can say not the most important sets in the whole field, but basically still they are like they're still important. Okay, let's go over them. Set of positive integers, z plus, they're denoted by z plus, z positive. Okay, raised to the power positive, something like that, is equal to, these are +1, +2, +3, +4, and so on. The set of negative integers, z negative, raised to the power negative, these are -1, -2, -3, -4, and so on. The set of odd numbers, are denoted by O, and they are like 1, 3, 5, 7, and so on. The set of even numbers, is 0, 2, 4, 6, 8, 10, and so on. The set of prime numbers, these are the set of prime numbers, 2, 3, 5, 7, 8 is not a prime number, 11, yes, 11 is a prime number. And basically what prime numbers are, prime numbers, okay, let's actually let's do this thing. The set of prime numbers, what is a prime number? A prime number is a number like for example 2 is a prime number. So a number 2 is a prime number. Why is that? Because it is divisible by itself. Okay, because it is divisible by itself and 1. So if I actually take out factors of 2, it is divisible by 2 and 1. If you multiply 2 times 1, it is equal to 2. Okay, 4 is not a prime number. Why is it not a prime number? It can be multiplied by 2 into 2, and it can actually be multiplied by 4. Like 4 times 1 is equal to 4, 2 times 2 is equal to 4. So that is basically why 2 is a prime number and 4 is not.